Okay.
Hello, welcome to Statistically Speaking. This is a bit of an experiment for all of us, and I hope that it's one that we're all going to enjoy. I started talking about having some statistics backgrounders with Marla a while back, and we found that although modern biology is getting more and more quantitative, we haven't seen as rapid a rise in numeracy education. Have you heard the term numeracy before? So you've got literacy, the ability to deal with words, and numeracy, the ability to deal with numbers. So I thought that it would be very useful if some of you got a refresher on statistics and some of you got a first introduction to statistics, because statistics seems to creep in everywhere in modern biology these days. The other thing is that I am not, specifically speaking, a statistician. I'm a bioinformaticist. So my specialty is in getting the most information we can out of biological data. Very frequently, that has meant that I needed to know something about statistics as well as something about the algorithms that we use for producing our information. So my goal today is to get started, to get us at a starting place for talking about statistics. And we'll have sessions, I forget, 11 or 12, something like that, through the end of the year to try to cover a lot of different topics in this space. So I'm really glad you're here. There's no grade for this. I see that we're taking attendance, but but that means you need to be in here, not necessarily that you need to learn. So I would rather that if I am blitzing right past you, that you stop me and say, I'm sorry, I didn't understand a word you just said. Because if I know that, I can stop, rephrase, reframe. And I would like you all to know as much as possible about statistics by the end of these sessions. So I am starting us with the CRAN, the Comprehensive R Archive Network. R is very, very widely used in the space of biostatistics, and I'm going to be giving examples in R as part of this. In fact, I only have something like 12 slides, so we're going to be moving to demonstrations live using R. If you have a laptop, it's really great if you can bring it. If you don't have a laptop, I hope you can borrow one from the division or something to work with. We'll make this just as accessible as possible. I have a spare laptop I could be bringing for that matter. But for now, I hope you'll follow along. Now, I know that we have a cameraman in the corner over here. He will be capturing a video of this session. I will be posting these on my YouTube channel. So they're not always the most brilliant video quality, but I do the best I can to try to get these lectures available in a reviewable format. So that you'll also have a link from the YouTube link to the text I'm using as my input for the script, and also for the slides themselves. So all of that will be available from the YouTube channel. We can point you to that. But for now, if you have a laptop, I would suggest that you download R for your operating system. If you're running a Mac, download the Mac one. If you're using Windows, grab the Windows one. The download can take a little bit of time. R has a lot of stuff built into it, as you will see. So if you're working without your laptop for now, write down Comprehensive R Archive Network. That'll be very helpful. I say this because a lot of people try Googling R, and if you Google a single letter, you don't get very far. So Comprehensive R Archive Network will get you the ability to download everything. Great. Okay, so with that said, I'm going to have a few slides where we talk about measurements and distributions. One of the things I always try to remember when I'm looking at a title slide is to introduce myself. I'm Dave Tabb. I am a professor over at Stellenbosch University's Tigerbird campus, the med school. So my specialty is dealing with proteome data, so data from mass spectrometry for proteins and to some extent for metabolites as well. But I also work as part of SATB, which is the South African Tuberculosis Bioinformatics Initiative. This is funded by the Medical Research Council, and in fact the Medical Research Council was responsible for my getting involved with UWC. They said, we're aware that they do an awful lot over there associated with tuberculosis and some that's not as well, and we want to see that they're getting bioinformatics and biostatistics training as well. So here I am. I hope that I can make a difference, and that statistics will not be your enemy. Much better than it be your friend. It's a terrible enemy. So let's get started with measurements and distributions. I chose this topic because biology has gone quantitative. I'm sure you may have noticed that senior biologists do not spend a lot of time running through meadows with butterfly nets. This is not really how things work anymore. Instead, we're more typically working with a pipetter or with our computers, of course, to try to make sense of the reams of data that we get back. All of these experiments that we do, all of the biotechnologies that we work with, produce data. And if you don't know anything about distributions, you may have some incorrect ideas about how to make sense of those data, to compare this set and that set, for example, to say, is there a difference or isn't there? So talking about distributions is just one of those central ideas that we have to talk about to get started with anything. And from there, we're going to spend a little bit of time talking about sampling and independence and identically distributed values. Because math, I realize, is not everyone's favorite topic. Do we have some people for whom math is a favorite topic? Oh, the room went dead. Okay, that's good. Well, so we'll try to do our best to be friends. You know, to make friends with math. Now, I've heard it said that Unix is a very user-friendly operating system. It's just choosy who its friends are. Math is the same way. And I appreciate that not everyone is going to feel intuitive and easy about math, and we're going to do our best to make this as visible as possible. So we're going to talk about logarithms, everyone's favorite topic, and exponential values as well, and compare those to the numbers we normally think about, linear values. And finally, we're going to have a little discussion of discrete versus continuous. Mostly, I want you to have these terms in the back of your minds for the rest of the discussions we're having because they show up everywhere. So with that said, let's plow ahead. So we're going to start with the uniform distribution. The uniform distribution is most commonly thought about in the context of a die roll, right? I have this die. It has how many different values on it? 6. It has 6 sides. I roll it, and the value 1 shows up. I roll it again. The value 3 shows up. Is there a greater probability that a 3 shows up than that a 1 shows up? No. What's the most likely value I get from rolling this die? Great. All of those probabilities, assuming this is a fair die, I could be loading it. I could be, but this is a fair die. So the chance of rolling any particular value on a single die is equal, 1 in 6. Okay? So this is an example of a uniform distribution. It's not what we typically think of as the uniform distribution in one important way. There are only 6 possible outcomes from a die. But from a uniform distribution, any value between the minimum and the maximum is possible. So I note that I have my standard die here, and I just want to highlight that the dice I brought in today come from a 1968 edition of the board game Risk, which was a huge classic in my family. Those more swearing has been exchanged over those dice than almost anything you could possibly imagine. But I also note that I'm a much bigger geek than that. I also spent a lot of time playing Dungeons and Dragons back when I was in Nashville. This is my character. He's Fundin. He's a dwarf. But we have all kinds of extra dice to work with in this case. So here I have an icosahedron. An icosahedron has how many sides? 20 sides. It has 20 sides. So when I roll this, I've just rolled a 10. Okay, so I have the possibility of rolling a 1 through a 20 on these dice. So we can think about slicing up this space. We started with 6 different possible outcomes, uniformly distributed. We now have 20 to work with, but as people will know, for particular spells, you need to have 1 of 100 outcomes. And for that, we have 2 10-sided dice. So I roll these, and now I see that I have a 30 over here and a 0 over here. So our total is 30 for this. So from a single die having 6 different outcomes to 20 different outcomes, slicing this probability up more thinly, we now have 100 different possible outcomes from dice. How many possible outcomes are there on a uniform distribution? Infinite. This is a continuous distribution of values. And here I've sampled from 10,000 values and plotted a histogram. Okay? So this is a uniform distribution. Any outcome is just as equally likely as any other. If you have enough samples off of it, you see this nice smooth distribution where any outcome is just as possible as any other. So the distribution is bounded. There's no value lower than 0 that's produced from this. And there's no value greater than 1 on this uniform distribution. So that's characteristic of the uniform distribution. Okay, now from that, I wanted to mention one other thing. This is a histogram, which means we're counting how many times values within a particular range happened. So we see that we had a slight increase in values just below 0.4. We had a slight diminishment in values just below 0.6. This is an empirical histogram of values we got in an experiment. When we look at the actual distribution, we say that the area under the curve is 1, which is to say that the only outcomes that we're going to see fall within this distribution, and they are, and if you sum together the probability of each possible outcome, you get to the totality of 1. So you'll frequently see that when you have different probabilities for outcomes, let's say the next time I have heartburn, it could be on a Sunday or a Monday or a Tuesday or whatever. So if I sum together all 7 days of the week, there's no other possibility. So the total probability is 1. So keep that in mind. Summing together all possible outcomes gives us 1. Now let's move ahead. Now we need to talk about normal distribution, or the Gaussian distribution. The Gaussian distribution is one of the most frequent models we ever see in any statistical test, frankly. So it's really worth your knowing. So I want to have a couple volunteers, if I may. Would you be willing to volunteer? All right, you get 3 dice, and you're going to get 3 dice. 2 closest. I'm sorry, you guys get picked on today. So, what is we said what was the most common outcome if we roll a single die? They're all equally likely. 1/6 is the highest and the lowest probability of any one outcome from a fair die. Now, however, we're rolling 3 die. So that's a little complex to think about. Let's think about 2 dice for just a moment. If I have 2 dice, is it just as likely that any possible outcome results? I have a head nodding yes. Well, let's start with an easier question then. What is the lowest value I can roll if I roll 2 6-sided fair dice? 2. It's called snake eyes. If I roll a pair of 1s, there is no 0 on the die. If I roll a pair of 1s, the lowest value I can possibly achieve is 2. Now, what if I roll the highest values? 12, a pair of 6s. Okay. So, are the probabilities of rolling a 2 and of rolling a 12 the same? Yes. Some no's followed by yeses. Okay, the probability of rolling a 1 has exactly the same probability as rolling a 2 or a 3 or a 6 for that matter. Are there multiple ways that I can get to a sum of 2 from a pair of dice?
No.
No. It means that each of them is locked in. This one has to be a 1 and this one has to be a 1. Is there any other way to get to 12 than having a 6 on both die?
No.
Okay. So that means that the probability of rolling a 2 and the probability of rolling a 12 on a pair of dice is the same. Now let's get to the harder question. Is the probability of rolling a 10, the probability of rolling a 10 higher or lower than rolling a 12?
Higher.
It's higher. Why is that?
There are more combinations.
More combinations, right. So I could have a 4 and a 6, I could have a 5 and a 5, or I could have a 6 and a 4. That's 3 times the probability of rolling a 12. Okay, so we started with a uniform distribution where any one outcome for an individual die was equally likely. It is not the case that when we add those together, any outcome is equally likely, because we look at the sum of 2 dice. So, will you be our will you be our recorder for a moment? Okay, I'm going to ask you to roll 3. Tell you what, I'll take those dice because you're typing. I'm taking them off duty. Okay, so please roll 3 dice. Okay, I see 10. All right, roll these. I see 14. Your turn again. I see 16. Good roll. I see 9. I see 9. All right, I see 9. All right, so let's stop right here. I'm going to stop right here. We've just seen the value 9 showed up 3 times in our first 6 rolls or so. Was it about 6 rolls? How many was it? It was 6 rolls, and we had 9 how many times? 3 times. Have I been sneaky? Have I brought in some special dice today? Okay. So, I want you to keep in mind that the rolls are independent of each other, and they're identically distributed. We're going to come back and revisit that theme. But for now, I want you to keep in mind that sometimes, especially when you have a relatively small number of rolls, you're going to get streaks of numbers that look like something unusual is happening. I know lots of us have played board games in our lives at some point. Have you ever fallen into the trap of saying, the dice have been against me all through this game? Right. The dice are not against us or for us. However, sometimes a small sample, another word that's going to show up a lot, a small sample of rolls causes us to recognize that. You know, in Dungeons and Dragons, if you're caught up in a fight and you roll a 20, you just beat the heck out of whatever you're fighting. You know, it's this amazing amount of damage you do. It's called rolling a crit, a critical damage. But, and one of the things that our brains tend to do, in science as in gaming, is notice coincidences. And we start to think, that's what's going on. The dice are against me today. Or I'm on fire today, when it's just the dice being what dice are. Okay? So that happens just as much in science as it does in games. I want you to keep that in the back of your mind. The dice are not for or against me. The variance in our experiments is not for or against us. It doesn't care about us. It's just variance. So, when we add together lots and lots of variation, one of the things that we frequently see is a distribution with a central tendency, right? So we have this big lump in the middle here, and we've got some trailing off to either side. That's an example of the Gaussian distribution. And the Gaussian distribution is a great way to model when you have a whole bunch of additive variance. That additive variance usually means that the values that come out have some central value and some spread on either side. So, a moment ago we said that uniform distributions are bounded, that they have a maximum high value and a maximum low value. That is not true of a normal distribution. This, again, is a histogram of 10,000 values drawn from a normal distribution. But if you looked at the actual normal distribution, you will see that it never really hits 0 on either side. It gets really, really close. So when we talk about spread next week, we're going to be coming back to this normal distribution to talk about it in more detail. But for now, I want you to remember that when many factors contribute to variance, the normal distribution is a likely outcome. So if I were to sort, I'm going to just start by splitting the class on gender, and then I'm going to sort you by height on one wall and sort you by height on the other wall. If I make a distribution of all of those height values, this is one of the most typical examples we ever see, we would see something like this normal distribution. Because there is some typical height for men in South Africa, and there is some typical height for women in South Africa. And people can be higher than that, and they can be lower than that. So there are lots of things that contribute to that. Genes, for example, if you come from tall parents, you're more likely to be tall yourself. Nutrition during your growth years, I mean, hey, I ate a lot, but I never really got big, right? So, we have all these different factors that lead to these things, and added together, they start to look like normal distributions. Now, it's also called a Gaussian distribution, and the reason for that is Mr. Carl Gauss, who lived in the time just after my country was getting started. I came here from the United States about a year and a half ago. So Gauss was one of the first people to really popularize this idea of a distribution with a central tendency and some amount of spread around it. Okay, so let us move ahead to one more. I'm not going to just go through all the possible distributions. If you go to Wikipedia and say, what are all of the distributions, you will see there are hundreds that we could be talking about. But I kind of like this one. Now, I don't think I have a light switch that I can flip here, but does anyone here have a kid? A child? Does anyone have a child?
Yeah.
We have a few people with kids. Do any of you have kids old enough to flip light switches? Ah. What is a kid's response when he or she is first old enough to flip light switches? Stop it! Okay, so the Poisson distribution is for you if your kid is flipping light switches. And the reason is that every time you apply power to a light bulb, you have some probability that the bulb filament is going to break. Okay, this is not true of LED lights or LCDs. But imagine the old school lights, the old Edison bulbs, right? So there's some probability that when you flip on the switch, you're going to get this really bright light and a pop sound. And that's the end of that light bulb. So what we have then is some sort of average behavior for these bulbs. This bulb is rated for 10,000 light switch flips. Or this bulb is rated for 100,000 light switch flips. Who knows? And when your toddler is suddenly flipping that switch on the wall, you're getting closer and closer to that time when that bulb is going to go away. But what we see is that these bulbs don't have a total failure exactly on the same number. They have a typical number of light switch flips that they can survive. So if you start with some number of these light bulbs, and you want to say how many of these are going to survive for 5 years, assuming that I turn it on and off 5 times in the course of a given day, a Poisson distribution is very good for you. So is it possible that the life of a light bulb is less than 1 switch under that model? No. Okay, it could be a manufacturing defect, but we're treating those as separate kinds of failures. So let us say then that zero flips to a break is not going to happen, but some number of breaks is going to be required before this event takes place. So we have a bound on this, 0, because it doesn't make sense to talk about negative switch flips. But we don't have a maximum, because some light bulbs, just by random chance, go on a lot longer than the manufacturer warrants that they will. Okay, so one of the things I would note is that there's still a central tendency on this, that you get more outcomes that are close to the manufacturer rating on that device. But some of them go on a lot further, and some of them go a lot shorter. So it's like the normal distribution in that it has a central tendency. But it's also like the uniform distribution in that it has a lower bound. So there are a lot of ways that you can use the Poisson distribution then to ask questions like, in a hospital with 1,000 light bulbs, each bulb rated for so many switch flips, what fraction will still be viable after a decade? You can answer questions like that sensibly with a Poisson distribution. It's one that I think more people need to know about, and it too comes from someone who started thinking shortly after my country was founded. Does anyone know, by the way, what Poisson means? Yeah, it's a French word for fish, exactly. So if someone ever says there's something fishy about your statistics, it probably means they're making a joke about Poisson distribution. Okay, on we go. All right, now we've mentioned sampling before, and sampling is certainly a very, very central concept in the space of statistics. So I really liked this image from Strategos Inc. I've tried, by the way, to cite every place I pulled an image from. Strategos Inc. did not specifically allow this to be reused in other people's talks, so I just recommend you go to their website if you want to learn all about their great products. But this image I think is just about the best I've seen on this score. I have some population of which I have some red beans and I have some white beans. But I want to make some estimate of what fraction of them are red, but I don't want to go through the awfulness of counting every bean in the world, right? I mean, that's just much too much work. So instead, I sample from that population a subset in some unbiased way, and then I count the number of red and white beans in just that subsample. So there are a lot of things going on here. I'm then going to conclude that in the larger population of beans, there's the same fraction of red beans as were in this unbiased sample that I drew. Now I had a whole bunch of loaded words in that. So think about this. We have a population. This might be household contacts of TB patients in a particular neighborhood of Cape Town, for example. We do a lot of TB research. We can't study every last one of those people, but we can sample, have some sort of selection process whereby we take some, we select as candidates some people we're going to follow closely into our sample. We learn from them. We create a model, in this case a fraction of that population of beans that are red, and then we try to extrapolate from that model back to the original population from which we drew. Okay, so what happens if I've chosen, let's say that I have a bias in my selection process. Maybe the white beans reflect light a little better, and so I'm more prone to sampling white beans than red. Now the model that I derive from the sample is biased towards white beans, and I cannot extrapolate that back to the original population without having errors. So having a bias in sampling is a really bad thing. Next, what if I chose an inappropriately small number of samples? Here we said we sampled 100 beans in the figure, but let's say that I only sampled 10. If I only sampled 10 beans, the accuracy of the proportion that I get out may be less generalizable to the population I drew it from, because I had too small an n. All right? If you have too small a number of samples, your model is probably less generalizable than one that's based on a larger population. If I sampled 1,500 beans from this large population of 3,000, I'm going to have a really good estimate of the fraction. If I sample 10, not so much. All right, so extrapolating is one of these things that we're trying to do. We sample a small number, from that we build a model that we hope relates to the original population. That is an extrapolation process. Okay, the n is the other thing that I really want you to think about. Have you got enough samples that the model you produce is going to be relevant to the population from which it's drawn? Okay, on we go. I'm talking an awful lot up here, but I'm going to try to make sure that we're talking to each other, because this is valuable. Independent and identically distributed. So imagine that I actually have a jar of marbles on my desk because I love this topic, so I always have that, but I didn't bring it with me today. So imagine that Dave is holding this really large jar of marbles. It has 900 white marbles in it. It has 100 black marbles in it. All right? So let us imagine that I have drawn 20 black marbles and 150 red marbles from this jar, and I'm holding those out of the jar. Is it true that the next marble I draw from the jar has just the same probability of being a black marble as the first one I drew? She's right. She's shaking her head no. The reason for this is that the marbles I've drawn out have changed the probability for subsequent marbles. If you have 50 people in your study, and all 50 people in your study are the only 50 people who have that particular disease, and you go running into the population for another sample, you're not going to find anymore, right? So the probability of what's available to draw from has changed. The probability distribution has changed. So these are not examples of independent samples, because we're removing from the jar as we pull each marble into our hands. All right, now imagine that I rolled a fair die 10 times, just one die. like that. Oh, I rolled a 6. How about that? All right, now in my rolls, I had 4, 4, 3, 2, 6, 3, 1, 3, 4, 4. It's not a phone number, it's okay. So, what is the probability that the next number I roll is also a 4? 1 in 6. Very good. You might be confused into looking at that and saying, well, gosh, 4 is the most common outcome. It happened 40% of the time, therefore the next roll has a 40% chance. Dice rolling is independent, as long as they're fair, and identically distributed. So when we work in our studies, when we're producing statistics for our research, it's really important that you keep in mind, are these values independent? Are they identically distributed? This is a phrase that shows up all over the place when statisticians are talking about the proper times to run a test. They will frequently say, can only be used in IID samples. IID. So, independent, identically distributed. IID. So if you see that phrase, keep in mind that somebody is making some assumptions that each of these values has nothing to do with the others. It's not dependent in any way on whether I've rolled 6s in previous rolls. Okay. Now I've included a little spot of R code down here. We're going to come back to that in a bit though. This is a biotechnology department, right? So maybe we should talk a little bit about biotechnology along the way. This is a figure produced by Andy Fierstreite in Belgium. So I've pulled it from his webpage. This is actually a really useful page describing how PCR works, if that has any mystery for you. So PCR is the photocopier of DNA. I think I'm going to assume that the people in this room have had some exposure to PCR along the way. So we use it when we don't have enough DNA for what we want to do downstream. So we use our photocopier, the thermocycler, and polymerase to generate a duplicate copy of every strand we've got. So we have one input double-stranded DNA coming in. We separate that by denaturing it, by melting it, and then we polymerize a complementary sequence to that. So one sequence comes in, 2 sequences come out. So what we can think of then is that this single template through one cycle becomes 2 templates. Or sorry, these 2 templates become 4 templates. These 4 templates in the next cycle become 8 templates. These 8 become 16 and so on. Whenever I'm feeling really stressed, like let's say somebody has shown up with a needle, I really don't like immunizations, but if somebody shows up with a needle near me, I frequently find that having something to distract myself is very powerful. Now lately, it's been talking about bacon cheeseburgers because they're never as good as they really should be. Think about it, bacon, cheeseburgers, these are tasty things, and yet we put them together, it never really meets its potential. Sorry, I get distracted on that subject. I like bacon cheeseburgers, but the promise is much greater than the punch. It's all right. So let's return to this topic then. What was that? Yes, PCR. One of the things that I used to do is try to remember different number series. So I was in the math club back in high school. I love that stuff. We would go to math tournaments every week. I was our story problems guy. So give me a story problem, I'm all over that. You know. But when I was getting shots in high school, I used to count off powers of 2. I've been a programmer for a long time, so that kind of thing always sort of appealed to me. So let's start our powers of 2 count. I'm going to start with 2 to the 0th power. 2 to the 0th power. Does anyone know what 2 to the 0th power is?
1.
You guys are so hot. This is awesome. Oh, right, yes. Any number raised to the 0th power is 1. Brilliant. Well done. So 2 to the 0th is 1. We multiply that by 2, we get 2. We multiply that by 2, we get 8, 16. Now some values that are not on the slide here. 32, 64, 128. 256, 512, 1024, 2048. It keeps going, right? 4096, 8192, 16536. After that I start losing it, but it's good. Sometimes knowing powers of 2 is really valuable as a programmer. So this is a process of exponential growth in the number of DNA sequences that are there. Now I want you to imagine that you're using a PCR-based detection system, right? PCR-based detection. So you have primers for some particular DNA, and you really want to know if it's there. We do a lot of work in Mycobacterium tuberculosis, so maybe I'm looking for any evidence that Mycobacterium tuberculosis DNA has been found in this person's sputum, right? Beautiful topic just before lunch, but there you have it. So I run PCR, and after each PCR cycle I ask, do I have any signal for this DNA I went looking for? I don't see it after cycle 3, I don't see it after cycle 4, I don't see it after cycle 5. I do see it, say, after cycle 12. Okay? So, what I want you to think about is if I write down as my measurement for each patient, how many cycles did I have to wait before I saw MBT DNA? Some of them might be, say, 12, some of them might be 14, some of them might be 30. That would be pretty wild, right? Some of them might be 8. So those measurements, although they appear to just be ordinary, plain Jane integers, in fact represent measurements of exponential nature. How much more DNA is there in someone with a score of 7, visible after 7 cycles, than somebody who is visible only after 8 cycles? We said that we double each cycle. So the answer is, there's twice as, if it's a perfect process, we have twice as much template in the person with a 7 cycle reading as they do with 8 cycle. So even though our measurements are cycle numbers that look like they're just integers, what they imply is exponential. So we have to be thinking about that. Exponentials are the inverse of logarithms. So we want to be able to think about whether our numbers represent linear measurements or they represent log measurements. One of the most common ones that we encounter is pH, right? We think about pH as being on a scale of, say, some very low number, say 1 to 14. But the reality is that these represent log measurements of ions. So a difference in pH of 1 is actually a 10-fold difference in the concentration of acid. So, of hydronium ions. I'm sorry, my chemistry is a little old at this point. But there are frequently cases where the values we're writing down represent logarithmic systems, not linear. Worth remembering. So, what is a log? All right. Now, you guys are already all over this because you knew right away that 2 to the 0th is 1. So maybe I don't need this slide. But just the same, I want you to remember that these top 2 formulae are telling exactly the same story. Log base A of B equals C. That is exactly the same mathematical statement as A raised to the C power equals B. All right. So these are the nature of exponential / logarithmic evaluations. So over at the right, I am using a natural log plot. I gave it values running from 0, well, just above 0, let's be clear, to 1,000,000. I gave it that as an input value. And then for each of those numbers I've asked, what is the log of that value? So we see that for these very lowest values that we gave it, the ones that are just barely above 0, we had negative logarithms that came out of it. When we got to even a very large number as an input, a 1,000,000 in this case, we see that our value still hasn't even hit 15. So logarithm is a function that we frequently use to try to reshape our data. You will sometimes hear people say, have you tried logging that distribution in order to make it work better with the statistical test? I want you to keep in mind that log has a different effect on the numbers that you feed it. That very large numbers are going to be reduced very powerfully. Now, a higher input is always going to have a higher log than a lower input. So you see that this curve doesn't fall down at any point as we move to the right. It's a monotonic up slope. The other thing I want to point out is that when you feed a log function a 0 as an input, you get negative infinity, essentially, as an output. So feeding zeros to a log system is not an appropriate thing to do. All right, and there's kind of this odd story about why the value e matters in logarithms. I did a little looking into it last night because I was kind of curious, and it boils down to a mathematician named Euler. Euler. I know it doesn't look like that. Did anyone see Ferris Bueller's Day Off? There's a scene where the teacher is calling roll, and he gets to Bueller's name. He says, Bueller? Bueller? So as a child, I often thought that this must be pronounced Euler, but it's not. It's Euler. So he did some research into this, and he wanted to have a natural logarithm. We think of log base 10 as something that we frequently use because we work with a base 10 number system. In computers and in PCR, as we just looked at, you might think of log base 2 as the natural place to work. But in logarithms, we ask what is the base that, when raised to the 0th power, has finally hit a slope of 1 in its curve. And that's what this 2.718 number is over at the right. So you will frequently see people write ln rather than log base 2 or log base 10. That's because they're using this number base. Okay, sometimes software will just do that without telling you. So, worth knowing. Okay, so we have measures that are continuous and measures that are discrete. And I want to make sure you have that separation clear in your mind. So if you're giving a measure of dimension, how tall is it, how wide is it, how deep is it, whatever, then that is probably a continuous measurement. It is possible for something to be 3.5 centimeters in size, right? It could be 3.443 centimeters in size. These are continuous measurements. They have arbitrary precision. You can go just as many points past the decimal as you'd like. Time is the same way. We say that it'll take me about a day to do that, but ultimately it may take you 23 hours, 57 minutes, and any arbitrary number of seconds after that. So time as well can be sliced up to any size you like. pH, we've already mentioned, is an ionic concentration measurement on the log scale, but it's continuous. There's no saying that something is pH 3 or it must be pH 4. There's plenty of room in between those. Temperature and pressure, obviously those can be sliced up just as narrowly as you like. However, we encounter lots of data types that are discrete. So one of the frequent things that we run into is counts. If you are working with data from a microarray, then you might have intensity measurements, which are on arbitrary units. But if you're working with, say, RNA-seq experiments where you've used a high-throughput sequencer, you have some number of counts to work with. So that's frequently the case. We run into count data in proteomics all the time as well. So it's a very common type. We often have categories or types or genders. We don't generally say that this person is 50% or 60% male. It's not something that we do. Likewise, dice rolls. So dice are inherently rounded. You're going to get this value or the next. So there's a problem in that a lot of times studies will model a continuous variable in bins. So let's say that you are looking at age of onset for TB. I know I use TB a lot. It could be HIV for that matter. It could be any number of things. So we might say that we have age 0 to 1 year. We have, say 2 to 12, and then we have 12 to 18 for the teenagers, and then 18 and up as another category. So this is a bin set that we've applied to this. And sometimes the way in which we set those bin boundaries has a big impact on our studies downstream. One of the things that bothers me the most about time series experiments is that people have these big gaps in their time series. They're not evenly spaced at all. And as a result, you end up with kind of these a well-sampled start and a poorly sampled end, for example. So Whenever we have to reduce a continuous variable into bins, into discrete values, we need to be careful because we're throwing away information. All right, that brings me to my closing thoughts. Our data come from distributions. Knowing a few of those key types is highly valuable to not making mistakes when you want to do statistics downstream. Dependencies among our data should alter our expectations of them. If my dice know what has been rolled before, if that impacts how they're going to fall the next time, that's kind of a strange thing. In biology, that happens frequently. So you can't assume that time point 4 for your patients is independent of time point 3 for those same patients. Do you see what I'm saying? Okay. Logarithmic expressions are common in biotechnology. Know how to interpret those. Remember that this is a key factor in understanding the values. When designing an experiment, limit the times that you record continuous data in discrete forms. Ages being lumped into inappropriate bins would be an example of that. Okay, now we are sitting at, 46 past the hour. I only gave myself 15 minutes to do R. So I'm glad that you have laptops here. I hope some of you have gotten the software installed. I'm going to move ahead to show you some of the things that you can do. And when I see you guys next week, I really hope that you'll have your laptops here as well, hopefully with R installed. I will make this video and the script that I'm working from available to you. So let us put aside our tool there for a moment. I am using some software called Emacs to visualize these results here. I'm going to show you how these execute. So when I have a hash sign like that at the start of a line, that means that I'm starting a comment in my code. So I'm going to start with the fact that we have variables in R. The first example that I've given is about as trivial as you can get. I have a variable A. I assign the value 4 to it. I have a second variable called B. I assign the value 3 to it. Could I say A equals 3? Yes. A equals 4? Yes, I could. But I'm using the assignment operator because it's very slightly cleaner and I'm kind of a pedant about such stuff. And then in the third case, I have set C to be equal to the value of A plus B, and I'm showing the result. So let's grab that code. We can work through this very basic example together. So I'm going to grab that. I have my R window running over here in the background. Oh, it's not going to show me the left edge of the screen. That's kind of rude. All right, well, let's grab that. And now I'm going to pull this. Oop, here we go. Over here. So when you run R, you may be running R Studio or you may be running R. I'm just running basic R. So R Studio is a little nicer. So when you run R, do you see something that looks like that? Oh, good, okay. So now I'm just going to paste that text in there. I appreciate you don't have it in front of you. I'll try to make those examples available to you in advance of the next gathering. So we see that the code executed without complaint, but when we gave it the value C all by itself on a line, it replied with 7. When you enter the variable name all by itself in R, it assumes that you just want to know what is the value of this thing. So I have C all by itself on a line, and as a result, it responded with 7. I also note that it's not 7 all by itself. It's got this little square bracketed 1 next to it. This is a hint as to where we're going with this, because R does not require that an individual variable name equates to one thing, one atomic value. You can have whole lists of things that a single letter points to. So it's saying that the first value associated with C is the number 7. All right. Let us now do a more complex example. We're going to use vectors this time. One of the most powerful things that you can accomplish in R, I'm going to just glom this into the text here, so you can type it from that window. So variables can also represent vectors. The C function that we're using here shows up right here. See this C with parentheses next to it? This is the compose or create vector function. I forget what it's called actually, but everyone uses it all the time in R, and this is because we have a list of things that we want to be offering to that variable. So A is going to represent 4, 7, and 3, B is going to represent 9, 3, and 6. C, we then tell to add these two together. So you can see that we're performing a lot of math all at once. That one addition operator applies to each of these values in pairs. 4 plus 9 is 13. 7 plus 3 is 10. 3 plus 6 is 9. So if you have long vectors of numbers and you want to perform the same operation on all of them, you could do that here. Some people have called this SIMD, S-I-M-D, single instruction, multiple data. Okay, so the C function then has the same function type, has the same kind of calling syntax as any other function in R. You have the name of the function, you have a parenthesis, and then you say what are the inputs to this function. So if I were simply to say C473, you see that its output is a vector of 4, 7, and 3. In this case, I've not captured that output. I've just had it sent it directly to the screen. So before I said A gets C473, and if I output the value of A, I get the same thing. All good so far? Okay. We're not going to do any really complex programming today. At some point we'll talk about how to do things like for loops and applying arbitrary functions across lists and nonsense like that. But for now, let's stay with simple stuff. Okay, now I want to point out that you're not limited to continuous values when you work in R. Okay, so here I have multiple functions all interacting with each other. So what's the output of just that C part? 1, 2, 2, 1, 1, 1, 2. Right? It creates a vector of those values. Now here, I have another function taking the output of the create function. So factor is a really special kind of thing. Factor is designed to recognize common values across a vector and assume that they are the same thing. So here I see that I have 1s and 2s all mixed together. If I'd thrown some 3s in there, it would have recognized that there's not just a 1 level and a 2 level, there's also a 3 level in there. So that this is a kind of a non-redundancy characteristic of this. If I have multiple 1s, it's going to include just 1 in the levels assessment. Okay, and then in this next stage, I have supplied another vector here, apples and oranges. You see that that together is just apples and oranges in one vector. Those have been applied right here as definitions for those levels. So the next thing I want to do then is to look at A after I've applied that levels function. You see what happened? The values in A started as 1s and 2s. But then later on, I told it, interpret every 1 as apples, interpret every 2 as oranges. So even though I started with 1, 2, 2, 1, 1, 1, 2, I have apples, oranges, oranges, apples, 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 oranges. So this is a really valuable thing. Frequently, when we're working on large spreadsheets of data from our studies, we use some sort of coding. For example, you might have a sex column for patients. So these are males and these are females. Now, what happens if you have a whole bunch of people all entering gender on the same spreadsheet? Inevitably, someone has a different idea of how to do coding. Maybe somebody writes males and females, another person writes M's and F's, and heaven help you, somebody writes 1s and 0s. So, having the ability to do mappings that are explicit to particular names, particular labels for these is very valuable. So this is an example where factors can be used to model discrete data. Okay. Now we're going to return to this. I wanted to mention one other thing. Plotting is a whole lot simpler in the world of R. So we have our vector A here of apples and oranges. If I want to see that graphically, I've got some default functions built in. Isn't that handy? So the software is clever enough to know that you've named the 1s and 2s to these particular fruit names. It's clever enough to be able to dissect how frequent each of those is in the population and produce you a nice bar plot for it. Okay, so that's very helpful. I'm going to close out that graph for now and let us return to this. So I have more complex code here. As I said, I'm going to make these scripts available for you to work with directly. So I'm going to start with the sequence function, the seq function there. We're going to give it values running from 0 to 1, and we've told it that we want it to give us 100 different values on this stretch. I don't want random samples from these though. I want a sequence of values. So if we were to look at the code that results from that, I'm going to grab just that little part of it right there. I can paste that in here. Oh, open this up full screen again. Oop. Okay, so we see that we have 6 values per row, 1, 2, 3, 4, 5, 6. So we have enough columns to compensate for all of those. We told it to give us 100 values running from 0 to 1, and there they all are. So this is one way to represent this sequence. Okay, now I wanted to compute what is the probability on a uniform distribution of each of those values. And that is the density function for the uniform distribution right there, DUNIF. There's another one for the normal distribution called dnorm, or for the Poisson function, dpois. So we're going to run this code more or less with that explanation. But I will say a couple things about this plot function. We are doing a standard dot plot on an x-axis and a y-axis. I've actually named my variables x and y here. I'm telling it that I don't want each dot to be shown independently. I want it to connect them with lines. So I'm calling it a line type plot. My eyes are sometimes a little bad when I'm looking at a projector screen from far away. So I want to have wide lines, line width of 2. And I didn't like just calling the y-axis y. I thought it would be valuable if instead we labeled that probability. So here I'm just going to issue that instruction, and now I can create my plot in R. Okay. So we see that our x values ranged from 0 to 1. Our probability stays right at 1 all the way across. We're not looking at a histogram this time. Now we're looking at the actual probability distribution. And remember that the area under the curve for all possibilities must sum to what? To 1. All right, so 1 over the unit space from 0 to 1 has an area of 1, right? Height times width, 1. Okay, so that's great. Kind of a boring looking distribution, but there it is. And the line is wide enough because of the LWD thing that we can all see it. So now I'm going to use the same for the normal distribution. But on the normal distribution, we're going to run from -4 to 4 using 100 values across that space. We're still going to use that as our input to the dnorm function. We're specifying that the normal distribution we're looking at has a mean of 0 and a standard deviation of 1. These are measures of spread. They're covered next week. And then finally, we're going to plot those. All right. I'm going to close that device. Okay. There we go. Nice and pretty, right? So that looks a lot cleaner than the 10,000 samples I showed in my talk, don't they? This is because we're showing the expected probability at each of those points, not a random sampling. Okay, I am running out of time, so I'm going to chop right to kind of the fiery business here at the end. Imagine that I wanted to get 10,000 rolls of 3 dice. Would your arms get tired? Mine would, and it would take a long time. The cool thing here is that we have the ability to simulate a die pretty accurately. So remember that our uniform distribution, oh goodness me. All right. So our uniform distribution can be used to generate dice rolls. So to try to walk you through this, I'm getting one sampling from a uniform distribution running from 0 to 1, so maybe it's 0.78, maybe it's 0.34, something along those lines. I'm going to multiply that by 6, and then I'm taking the ceiling. This is not something that you talk about a lot in math classes, but we often think of using a round function to round up if you're past 0.5 and round down if you're below 0.5. Floor and ceiling have special meanings like that. In a floor function, you always truncate off everything past the decimal point. In a ceiling function, you take only you always round up. So here I had values, say, from 0 to 0.15999, all getting rounded up to a 1 because they've been multiplied by 6. All right, so that function gives us a simulated dice roll. Here, I'm now going to simulate 10,000 rolls of, I said 3 dices, what was I thinking? Okay, here, we'll get rid of that. 3 dice, is that better? I don't know if you guys are picky about language, but I am picky about language, so, all right. So we're now going to run this, and you see that 3 dice is simply going to add together the value of A, B, and C at each of those 10,000 locations. So is this going to take a few seconds to run? It's not. Computers are so fast these days. So here we go. We now have 3 dice that we're adding together. This is what that distribution would look like if we just kept rolling and rolling and rolling these out for 10,000 times. You can see that the most typical value we saw was about 11 to roll 3 dice together, which makes sense, really. What is the minimum value you can get when you roll 3 dice? 3. When you roll 3 dice, it's 3. And when you roll 3 sixes, you get a 18. Okay, so that's a pretty picture of it. Let us also interrogate that object a little bit. So remember that when we created a histogram by itself, we get a picture to look at. But we can also capture that information by instead storing the histogram output to an object we'll call H here. Oops. Let me close that image again. Copy, close twice. It keeps maximizing and minimizing here. All right, so I've now stored the histogram object into the letter H as a variable, and I'm just going to run H. See that? So at the top, I'm sorry, it's actually scrolled a little bit past what I wanted to show. Okay. Remember in Excel, if you try to do a histogram, you're just in for a whole afternoon of unpleasantness. Here the software has figured out things like, where should we break up this distribution for plotting? And you see that the first category it has is a 3, representing a sum of 3 ones. And we see that that happened 196 times. We had the highest value we saw was 18. We see that the count of times that it appeared was 56. So all of this information that went into the plot is also available to us as the object created by the histogram function. So this is a really nice bit of stuff that you can do with R, and we're going to have a lot more fun with it as the weeks continue. So I don't want to take any more time today, but thank you very much. I hope this is useful to you. Next week we'll do more interesting things, so I'll look forward to seeing you then.